Thank you very much. It's an honor to be here to kind of close out the technical session. Hopefully this will be an interesting discussion, and I think it addresses a lot of the questions that have been asked today. So I'm Ted Bapty. Thanks for the introduction, and I'll talk about the Metamorphosys tool. Okay? Slides. So I'll go through a few slides, and then I'll give you an actual demo of the tool. So if you were here this morning, you heard Regina's very inspirational talk about the process of design tools and the history of design as it's gone through from the early Apollo program all the way through up through current time. And she presented this chart, or an abstracted version of this chart, and noted that we see these patterns in the design where errors are discovered only after a physical build. So we see 4 different prototype builds here, and actually seeing increasing number of errors discovered as time goes on. Not a good pattern. If we tease this apart a little bit more, we can look at some of the issues associated with this, and maybe learn a little bit more about the different colors represent the different domains and the different types of teams. We have mechanical, electrical, and software. And one very interesting thing to notice is the mechanical and the electrical are totally out of phase, opposite. Also, the software team in blue there doesn't discover their problems till very late in the design. So I think this shows an issue, or shows part of the issue, that these teams are working independently and the domains are handled independently. Unfortunately, the world is not nice. It does not let us separate everything out into nice, clean boxes. Things do occur. These systems interact. So decisions that one team makes can have bad impacts on assumptions that the other team makes. And if you don't discover that until you put it together, then you can run into real issues. So these issues occur in terms of modules overheat, software is laggy, noise impacts on the system. So we venture to solve these with the tool and the work we're doing with the Metamorphosys tool chain. So how do we solve these things? Well, in short, a couple of things: abstraction, automation. So we're working on abstraction for separating out the concerns or managing the concerns of the team, and then we're also building a tool set around building that, automating that process, and an open source tool set such that it's available to every one of the designers out here at very low cost. So we handle abstraction in 2 different ways. One is design level abstraction, design detail. So working instead of with tiny little components, millions of connections, thousands of connections, millions of lines of code, you work with larger blocks that encode the details, such as you've heard on all the presentations throughout the day, of all the details that are very, very necessary for this system to work, but not necessary for you to see at every step of your design. Second, we abstract domain details. So by composing all these together in an executable form, we can address the mechanical, the electrical, the RF issues all in one shot. So that's kind of the abstraction story. Automation is being able to perform a full open source, a full integrated tool flow, so that it's not a lot of work for you to manage 10 different models for your system. A single button being able to drive this whole process, to be able to run all your tools without 10 different teams specialized in each one of these tools. One model drives simulation, analysis, printed circuit boards, CAD, FEA, RF analysis. By integrating these best-in-class open source tools and also commercial tools as well, we can make a toolkit that can operate at low cost and high fidelity, and allow us to perform virtual integration at every step of your design, hopefully eliminating the prototype cycles. We'd much rather see a single 4 different modules produced with a single prototype than one prototype developed, or one module developed with 4 prototype cycles. So this sounds great, but why is this not already done? The answer lies in semantics. So we have lots of these different tools have evolved with different semantics focused on the way these different domains operate together. So if you think about the digital domain, they deal in ones and zeros, discrete time, discrete event, ones and zeros, clock periods, discrete event solvers. Analog design is in continuous time, continuous voltage, or continuous time, continuous value, voltage and currents, and requiring partial differential equations for a solution. Physical deals with geometry, the constraints on geometry, partial differential equations for FEA. So very different domains, very different ways, very different types of models that you deal with that. So these semantic gaps are the barriers to integrating these tools into a common flow. So what we've done is we've come up with a semantic integration language that focuses on capturing the components, capturing the pieces of these without the individual semantics of these domains without replicating it. So we're not making one big ball of semantics that is an impenetrable model. We capture just what's necessary, wrap it, and encode that into individual components. We also focus on how to compose these components into systems so that it allows us to map from your common single model down into all the target tools in a way that retains the correctness, retains the intent of the design into that specific model for that specific domain. This allows us to have that one model and perform the virtual integration using that single model. So where are we with our tools? So the Metamorphosys tools address all the phases and abstractions that should be required for an Ara module design. So in the architectural space, we have architectural modeling and design space modeling, allowing you to specify flexibility in your design. And then some simple tools that will assess the physical fit of the tool. Does your module fit into a 1x2 or a 1x1? And also, what is the cost? So those are simple analyses. When we talk about the behavior of the analysis, we have tools to analyze the analog, the digital, the software, and be able to integrate those together to let you assess your system before you build it all the way through. For the physical, we flesh out the details associated with printed circuit boards, help you do that, and then also build the CAD models to check for interferences, and then perform the finite element and RF kind of analysis requiring the physical three-dimensional world analysis. Production and manufacturing, making the manufacturing files that you need to produce your module, and you heard earlier about the TDP process to produce the technical data package that you need to submit to get your module into the Ara store. And of course, on the left, all the content. So these are all the blocks that you'll use to design your module rapidly. And I think throughout the day, I probably counted 100 different IP modules that were discussed in great detail. That's absolutely necessary for this system to work and for it to work efficiently. But I would much rather just replicate what Ara and Seth have done than understand every last technical detail, because I want to get my module done. So including this complex IP, including this high-level abstract content, I can rapidly combine that together from the modules and the component suppliers. So rather than kill you with PowerPoint or Google Docs, I should say, I'll give you a rapid walkthrough of the design process where we'll go through a full module design and exercise some of these tools to produce a module. So in this example, I want to build a little microphone array module where I can sit in a crowded room and direct my microphone, a virtual microphone, in a specific angle using an array. I like it to fit in a 1x2 module. I want it to be cheap enough that I can sell it on the market very inexpensively and make a profit. So to accomplish this, I need to design it. I'll need analog. I'll need sensors. I'll need a local processor to perform some onboard DSP. and I'll need all the Ara content that lets me conform to the MDK. So that's all the interfaces, all the physical properties, everything you've heard about here in the past day. I'd like to go single cycle to a prototype, such that I get my engineering prototype when I'm ready to manufacture. So I want to be able to do analog digital analysis, get my software running before I build it, and produce a PCB. And I also want to maintain some design flexibility so I can adapt my process, so I can optimize it, and so I can also move my product along with the different spirals, so I don't have to do a major rework each time. So, given that, let me start up the video, and I can try to keep up with the video overlay. So this is the walkthrough. Elapsed time is about half an hour or so. So this is the Metamorphosys tool. I'm using the architecture definition. I'll design a point design. I'll bring in the Ara interface. That's the whole block representing everything I need to do to interface to the module. I have brought in a digital subsystem. I brought in an analog subsystem, my microphone array, and then I bring in the templates for all the mechanical and printed circuit board for a 1x2. I bring in a simple display circuit, and then I need to wire them up. So these are very abstract connections I'm making. These represent buses, power buses, digital buses, analog buses. And then connect it up. I'll do one more thing, bring in a little monitoring circuit, and then I'm basically done. So about 5 minutes, I have my module done. Now, that's easy to say, but what's really under the covers? Well, I have a lot of IP. Someone designed a microphone array for me. This is the Spiral 1 MDK data for the Ara interface. So I'm just leveraging that content. So I included a lot of chips. Now I want to find out, does this really fit on a 1x2? So I'll bring it into one of our analysis things. We call them test benches. They're really the composition engines. I'll compose do a place and route for this board. And there's my module. You can see it's a Spiral 1 because you see the big EPM. You can see my microphone's on there. Everything fits. Looks like it's got some space. So I'm happy. Now, does my analog circuit work? So I'll use ngSpice and a visualizer to run some simple simulations of a microphone analysis. So again, bring it into the test bench. This is a simple one. All I do is connect up power, but I could also connect up signals and other things in there. And I'll go tell it to synthesize. So while I was talking, the window on the bottom synthesized it. The window on the right is my generated net list. And the software, the tool, wrote all that Spice net list. I'm glad I didn't have to write it. So it ran the simulation. Let's go through the browser. We'll look at the output of the microphone. That's what's expected to generate a signal. We'll go through and look at the output of the amplifier. And oops, I have distortion. The headroom on my op amp's not big enough, chopping my signal. I don't want to build that, so let me go back, look at how it's implemented. I see I have a gain and an offset resistor. I can adjust those. I'll bring some parameters in and tell the system to change the values from 22K down to 10K, wire them up. With another push of button, I'll rerun that simulation, generate a new Spice, kick off the Spice simulator, and wait till it tells me that it's ready to compute all the currents and voltages in there. I can go back and examine my circuit again. I've sped this up a little bit. It took about 3 or 4 minutes to run the Spice simulation. So navigate down, find the microphone output. Yeah, that's expected, and look at my output of my new amplifier configuration. And sure enough, it looks good. And I can go through and look at all the other channels, which exact same circuit, so they're as expected, no distortion. So I've solved my analog problem and ready to move on. Now there's the issue of the digital design and the software. I've got firmware and I've got an app. So I'll bring my module in and I'm going to generate an emulator for my system. We're using System C, which is a discrete event simulator, and we'll go through and we'll compose the simulation for this analysis for this module. So I've got an Mega on there, and I've got well, at Mega for my firmware, I'm using an Arduino sketch kind of environment runtime here. You can see the, if you've used Arduino, you see a familiar looking setup and loop construct. And then we can go through and see, I'm sampling all 4 channels. I'm doing a little bit of checking on it, doing some digital reads and writes. And then down at the bottom there, I'm writing out to the I2C port so I can send the data up to my module. This is not a full analysis. I'd need to do my beamforming and all that stuff. But for purposes of a demonstration, that's what it. So this is the overall System C program. It composes all the different components, all the models from all the assets that I've used. I kick it off and run it, and I can see the events occurring. I can see the timing of everything, and I have a little monitor, a little logic probe kind of device over that shows me the output on my digital bus. And I can also kick off my Android app, and that we have a bridge that connects up to the Android app, and I can run that under the emulator, or I can run that under a real physical device, connects in through the TCP port, presents kind of an abstraction of the high-level gray bus protocol. So there I am. I can rerun this and develop my software right on my desktop. I can also take the results of that simulation, they've been logged, and go and dig down into the circuit. So on the top line, I have my analog ports. I'm going through and selecting out all the digital ports on there, and I can see exactly what outputs I generated at what time, do some fine timing measurements, and really do kind of a post-mortem on this. I can also go and look at the processor state. So if I'm worried about keeping the low power version of the region of the processor, I can optimize my process. So that's kind of the software. Now let's go through and we'll do a place and route on that board. I'm ready to just take this point design and implement it. So I'll bring my circuit into my schematic test bench and tell it to generate. So just like I did the place and route, I'm doing an auto placement on the device. And I'm also, I can also put constraints and tell, like the EPM needs to be at the top of the board, things like that. So I'm generating, I generated the place, generated an EagleCAD, and told EagleCAD to kick off and run. I also generated a CAD model, so I can look at how my circuit's on there. And I've generated other CAD models that have the shield on there and that have the bottom case. And I can look at that and I can see I do have a problem. My board is a little bit too wide. It's interfering. So I need to go back and fix that. What about cost and availability? We had a question about that earlier. We generate a BOM. We'll go out and query Octopart for all the parts availability and cost. I can give it the quantity that I want to build. I'm saying for the first time I'll do 10, quantity 10. Go out and query the net. And tell me I want to know how much is this going to cost, and I want to know where I can get the parts. So $23 is what it says here. Now, in this, the question earlier was about the Ara specific parts. We'll be putting those into the system. They're not in there right now, but it tells me where to find that, where to go to DigiKey, what the DigiKey part number is, and all that. So now I want to know, well, what about if I build 10,000 of these when I go to production? What's my volume discount? $14, so I've got a much better price. I can evaluate, is that good enough or not? If I want to optimize, I'm using that Mega processor. There are lots of different ones. We can use the concept called a design space. So that's this little dotted construct down here where I put in multiple equivalent circuits or chips, components, and I put that in place of my single point design of my Atmel processor. Now, this is shorthand to say this is really 7 different designs, since I have 7 options in there. There I've elaborated them out, and the system will actually go and compose those 7 different models, and I can run that through any of the analyses. So here, just because it's most visual, I'll go through and I'll generate 7 different printed circuit boards. So if you guys used EagleCAD, it probably took you longer than 30 seconds to build 7 of them. But for me, it took me about 30 seconds. So I'll kick that off. We'll get them to run. And this is obviously sped up a little bit. Auto place all of them. I can see, see what happened, and choose the best design for this, for this option. I would also need to do the SPICE and the System C and all those things as well. But again, it's the automation. Any of these designs can go to any of these targets, and I can rapidly use the power of all the tools. So what if I want to adapt my design? So I come along and say, well, this is great, but what if my hand is shaking and I want to stabilize that beam? Well, I can go to the component library and look around and find parts. Here I'm looking at my sensor library. I've got accelerometers, I've got gyros, I've got IMUs, got all kinds of things that you'd find, and really we took things that were on SparkFun and put them in here. So I'll go and grab that and bring it into the module, and I need to wire it up, obviously, wire it up to power, wire it up to the analog ports, use the ports, I think I chose 7, 6, and 5 for my analog outputs. And now I have a new design, a new abstract design. I can take that, run it through the whole spectrum analysis using the automation, and then build the thing. So in this case, I'll also just go directly to the build, bring it into the schematic test bench, and generate a new design. And in a matter of minutes, I have a new design that's updated for that new requirement. Obviously, I'd need to go and write the software, test the software, tweak it, and all that stuff. But you get the point. Now, what about evolving the design from Spiral 1 to Spiral 2? Well, a couple of weeks ago, we got the Spiral 2 stuff. We put that in as a component block, replaced the Ara interface, or put that into a design space. And now I have 2 different designs here. And you can see, it's kind of interesting, you can see all the free space in the Spiral 2 module. It kind of reinforces what we've heard about earlier. What about evaluating the physical properties? Roshni talked about the RF analysis. That's the open EMS on the left. It's just doing a power evaluation of some operations occurring as it goes through the different RF modes. On the right is a thermal analysis. So we had a question about that as well, evaluating the progression of thermal using the data that I got from my System C, from my analog spice, the power I got, to determine exactly how my board is going to progress thermally over the time. So in this time, you've seen me build a design from IP. I've evaluated and fixed an analog problem. I've evaluated my digital digital hardware, and built a platform to develop my software. Built PCB, bill of materials, explored alternative chips, expanded functionality, and built both Spiral 1 and 2 designs, and started to address some of the physical properties of the system. So this is all in the Metamorphosys tool, and all in a very, very short amount of time. Probably half an hour or so I've gone through a lot of these different analyses. So if I could have the slides back. And this is my final slide, one more. So as I mentioned, these tools are open source. They're available for download. You can see the installers, the sources, and the docs are available there. You'll probably want to use the installer. This is a Windows desktop installer. But if you're interested in digging into the tools, we'd love to have people dig in and add things to the tools and add additional functionality. If you have a tool you want to put in here, talk to us, absolutely. And also there's some documentation. Now you notice these were Windows-based tools, Windows desktop tools. We are also migrating these things to the web to give you a zero install, better user experience, and also give you a little more power of sending these jobs out to the cloud, especially when you get into the open EMS. Those are a little compute intensive. We have a very early view of that. It's mainly just an editor and a little bit of schematic generation, but we're moving the power of the tools or the features of the desktop into the web, and that will probably be 5-6 months before we get that fully up to speed. But the desktop tools are available. Also, I invite you to come and join our beta test program. We'll be working a lot to help you access the tools, use the tools, and use them in designs of your module. And we expect to learn what you find important, what you find good and bad about the tools, and adjust the tools as we go forward.